Hello, this is David Scher. I'm recording this video near the end of the semester. Someone asked me about posting solutions for the calculation problems from the second midterm exam. Uh, and I thought I had done them in class, but that was for a different class. So I'm going to record now calculations for the or how I would do the calculations for the midterm exam uh, or that require calculation. As I said, the problems that require calculation. So let me share my get things ready, and I'm going to get things set here so we can do this work. I'm going to share my screen. Okay, this is midterm 2. I'm going to open it up and start signing as I'm going to take the exam. Okay, and so now I'm looking for questions that require calculations. It looks like question 7 is one. So here it is. We have a point source, 20 megabecquerels. It says there's 1 photon per disintegration. Energy is 1.5 MeV. What's the photon uh, fluence? The flux. What's the photon flux? So phi is equal to the the decay rate, 2 times 10 to the 7th, is that right? 20 megabecquerels, 2 times 10 to the 7th per second, divided by 4 pi r squared. R is 1 meter. So 2 times 10 to the 7th divided by 4 pi. And this is in units of per centimeter, 100 centimeters squared. That will give us units of per square centimeter per second. So that's going to be right. Let's get our calculator out here. On. All right. Oh, I didn't change the screen to show you my calculations. So let's get to it here. There we go. So, as I said, we had 20 megabecquerels, 2 times 10 to the 7th per second. 4 pi r squared is the solid angle for all the way around a point source. So 2 times 10 to the 7th, 4 pi, it's 100 centimeters squared. That will give us units of per square centimeter per second. So get our calculator out, as I said. 2 times 10 to the 7th divided by 4 divided by pi divided by 1 times 10 to the 4th. So if I have 100 squared, that's 10 to the 4th. And so that gives me an answer of 159.15 per square centimeter per second. Okay, so that was the answer, 159.15. Now let's go back to our, that's it. Yeah, that's it. Now question 8 is very similar. It's the same thing, 1.5 MeV photons, 20 megabecquerel source. This time I give you the fluence of 1.59, 15 per square centimeter per second. So I took the fluence that I had calculated for the first one and used it the second. So I want to know what is the uh, absorbed dose rate, right? Absorbed dose rate. So D dot is equal to, so to get the absorbed dose rate, it's phi times E times mu En over rho. So phi we just figured out, 159.15. E is 1.5 MeV. And let's figure out mu En over rho for 1.5 MeV photons. So 1.5 MeV photons, that's 1.5 MeV. This is mu En over rho, 2.54 7 times 10 to the minus 2. Okay, let's get out our calculator. So I still have that 159.15 still in there. So I multiply by 1.5 MeV times 0.02547. 0.02547 on the screen. And I hit equal, and it's 6.0 MeV per square centimeter per second. That's what the units. Oh, no, excuse me. That's not correct. It's so this is units of per square centimeter per second. This is grams per square centimeters per gram. So that's wrong. So it is MeV per grams second. That's what it is. MeV per grams second. Okay. So 6.08 was the number we wanted to be. Let's see what else we have to calculate here. Let's go no calculations. One word answer. Identify the values. So you can see the answers to these in your completed questions. So we need to go to, let's see. Oh, there's some answers to be done here. 14. So the question is, which entry do I need to go to find out information about the LUM classes? This is what I was looking for. You have to go to plutonium-234 to find out which compounds are W and which compounds are Y. So that's what the question was intended to ask is, where do you go on the table to find out information about what compounds to include here? And that is a different isotope. What's the critical organ for this nuclide? Okay, and this was, let's see, everything has bone surface as the critical organ. So bone surface. I'm going to ingest 1 microcurie of plutonium-240. What would this committed dose equivalent to the critical organ be? So we're doing ingestion, oral ingestion. The dose coefficient is 0.8. So if they ingest 1 microcurie, that is 1 divided by 0.8. So they have, well, I did times 1 divided by 0.8, 1.25 times the critical dose organ. And what's the limit? The dose limit for the critical organ. 1.5 times the dose limit for the critical organ. And the dose limit for the critical organ is 50 rem. The dose limit for the whole body, or the effective dose equivalent, is 5 rem, but for the organ it's 50 rem. We have 1.25 times that, 62.5. So this was 8. So this is 14. This is part C is 62.5 rem. So what's the committed dose equivalent to the someone adjusted 1 microcurie? What's the committed effective dose equivalent? So the whole body. So instead of using the one for the critical organ, I use the one in parentheses. That's the one for critical for the whole body, the committed effective dose equivalent. So that's 1. The alley is 1. They ingested 1 microcurie. So it's going their dose to the effective dose equivalent is going to be equal to the limit. The limit for the committed effective dose equivalent is 5 rem. I'm going to move this over so you can see my writing. Here's what I did the problem before. I just multiplied it out, and I got 62.5. I didn't realize that I was covering it up. So those are the calculations I did before. Phi E mu E N over R. Now, it's 5 rem for part D. If I can go back up here and find it. Okay, that's it. So I've got A, B, C, D. The ingested 1 microcurie. The alley is 1 microcurie. It's for the whole body, so it's 5 rem. So that is 5 rem. If someone ingested 1 picocurie of soluble, so class W 240, what's the effective dose equivalent? So if we're talking about class W and we're now inhaling, there we go. Inhaling class Y. Inhaling class Y. And I've got critical organ. So class Y right here. Critical organ is bone surface, 0.02. They inhaled 1 microcurie. Is that what it was? So 1 microcurie times. So for an organ, it's 50 rem per alley. It's going to be a big number. Oh, this is picocuries, not microcuries. So it's 1 times 10 to the minus micro, nano, pico, 10 to the minus 6 microcuries. So 10 to the minus 6 times 50 divided by the alley, 0.02. 1 times 10 to the minus 6 divided by 0.02 times 50 rem. 0.025 rem. Okay? Because it's picocurie. Okay. So that was E. And part F is the same thing, 1 picocurie. Class W, and this is the whole body committed effective dose equivalent. So we're talking about class W, and because we're interested in the committed effective dose equivalent, not the organ dose, we use that. Same thing. Alley is equal to 0.01. So I have 1 times 10 to the minus 6 microcurie times 5 rem. It's CEDE limit, not the organ dose. It's the whole body. And the alley is 0.01. Well, this is going to be easy. So this is going to be 5. This is going to be 10 to the minus 4 because 2 of the decimal points go down there. Or erase for that. So 5 times 10 to the minus 4. 1, 2, 3, 5 rem. Oh. G. What's G? Worker exposed to class Y for 10 hours at a concentration of 7 times 10 to the minus 10 microcuries per milliliter. So C equals 7 times 10 to the minus 10 microcuries per alley is equal to, this is class Y, excuse me, not alley. We're interested in the DAC. We're not interested in the alley because this is an airborne concentration issue. This is committed dose equivalent to the critical organ. Okay, the dose to the critical organ, DAC for the critical organ, is 7 times 10 to the minus 12 microcuries per liter. dose up there, or units up there. So C over the DAC. And what's the time frame on this? 10 hours. So let's do this. DAC hours equals 2 times the DAC, because it's 2 hours. 10 hours. 10 times the DAC. 10 hours. 10 times the DAC. 7 times 10 to the minus 12 hours. No. Yeah, that's not correct. That's not correct. I apologize for wasting your time. The concentration, the DAC hours, equal to the concentration times the time divided by the DAC. So the concentration is 7 times 10 to the minus 10. The time is 10 hours. And the DAC is 7 times 10 to the minus 12. That's the DAC, the dose in DAC hours. So that's going to be equal to 7 times 10 to the minus 9 divided by 7. The sevens are going to get rid of each other, but I'm going to just include 9 divided by 7 times 10 to the minus 12. It's going to give us 1,000 DAC hours. Okay? Now 2,000 DAC hours, so 1,000 DAC hours times, this is for the critical organs, so that's 50 rem for 2,000 DAC hours. So it's a half, so it's 25 rem. So that's part G, 25 rem. H, we want to do the same thing, but for the whole body. Okay? So we have to go back up here and see how we're going to figure that out. Well, the DAC, the alleys are the same. So the DACs will be the same. The DAC for the whole body is 7 times 10 to the minus 12. The DAC hours is the same. We still have 1,000 DAC hours because we have the same DAC. So C times T over DAC is still equal to 1,000 DAC hours. But 2,000 DAC hours is now 5 rem. So 1,000 times 5 rem over 2,000 hours. 5 rem for 2, because it's a whole body exposure. That's the whole body limit. So it's half of that is 2.5 rem. And that's the answer we got. Okay, so now I have to scroll on down. What's the next question with calculations required? That's a long answer. 17, environmental sample. It's counted for the counts, the sample counts. You go to 2350. Sample time is equal to 10 minutes. Background, the background counts is 142. And the background time is equal to 5 minutes. Okay, so what's the net count rate? 2350 over 10 minus the count rate from this one, 142 over 5. Well, that's up 23.235. What's 142 over 5? That's the same as 284 over 10, 28.4. Right? I just doubled that. It's 284 divided by 10 is 28.4. If I subtract those two, I get 206.6. And this is counts per minute. Okay, so let's do this, finish this up. So that's what the net count rate is. Now I want to know 17. We want to know not the counts per minute. We want to know what the activity is. It's counts divided by the efficiency. 206.6 divided by 0.3. 668, 688.7 dpm. Now we want it in becquerel. If that's how many is in a minute, there's 60th. That's per minute, so there's 1 minute. We'll get the minutes out of the bottom, and there's 60 seconds. So divide this by 60 seconds, and I get 11.4. Okay? 11.48. Just in case we want another number. But something like that. Okay. That's the next one. And we got a calculation for number 18. 17. Number 18, we have to do the standard deviation. So the standard deviation is we take the count rate is that. That's how we get the standard deviation. So the count rate was 235. The time was 10 minutes. The count rate was 28.4 over 5 minutes. Take the square root of all that. 235 divided by 10. Okay, that's 2.35, makes sense. Plus, it's 28.4 divided by 5. Everything inside that radical is 29.12. Take the square root of the answer that I just got, and I've got 5.40. That's counts per minute. And then to get the activity in disintegrations per minute, divided by the efficiency, divided by 0.3, 18 dpm. That's disintegrations per minute. And if I want disintegrations per second, again, I divide by 60. And I get, divided by 60 seconds, equals 0.3 becquerel. Okay, and that's the answer. I believe that was all the, let me see any more. That's all essay. So we are done. That is everything. I thank you for your time. I hope this was helpful to you. It's going to be on the website for you to look at.